Sometimes the easiest way to prove something is a proof by exhaustive cases. So here's an exercise from your Rosen book. It is prove that there is no positive integer n such that n squared plus n cubed equals 100. So again, that's prove that there is no positive integer n such that n squared plus n cubed equals 100. Okay, well the first thing to notice, and you can figure this out by using your calculator, is that if n equals 5 and you raise it to the third power, you get 125. Okay, so if there is some n that satisfies this equation, n, we just proved that n has to be less than 5, right? Already 5 is too large because 5 cubed is 125. So we can just start checking. How about 4 cubed? That's 64. And what's 4 squared? It's 16. That's 80. So n equals 4 doesn't work because 4 squared plus 4 cubed is 80. How about n equals 3? It's 3 cubed. I guess I don't need a calculator for that. 3 cubed is 9. 3 cubed is 27. Maybe I do need a calculator. 3 squared is 9. 3 cubed is 27. So when you add them, you get 36. This doesn't work. What about n equals 2? Well, 2 cubed is 8. 2 squared is 4. So 2 squared plus 2 cubed equals 12. That doesn't work. And 1 squared is 1. 1 cubed is 1. 1 plus 1 equals 2. That doesn't work. So no, there is no positive integer n such that n squared plus n cubed equals 0. Our first step was to notice that n has to be less than 5. And then we exhausted all the cases for n less than 5 to show that it just can't possibly work. Another example of the same flavor is, this is again another problem from your Rosen book. Prove that there are no positive integers x and y such that x to the fourth plus y to the fourth equals 625. Okay, so again we can kind of take out our calculator, and what if we let y be 5 and we raise it to the fourth power? Well, we get 625. So 5 to the fourth equals 625. So if y is 5, x has to be 0 for this to be a solution, but we said that x and y both have to be positive, greater than 0. So if y is 5, then x has to be 0, and this doesn't work. We need both x and y to be greater than 0. Okay, so y equals 5 doesn't work. How about y equals 4? Well, if y equals 4, 4 raised to the fourth is 256. This equals 4 to the 4. And then, well, I guess we could take, well, we can't take x to be 5 because that'll be too large. We'll be adding 625. So if we take x to be 4, then again we'll 4 to the 4 equals 256, and so we'd get 256 plus 256, which equals 512, and that's less than 625. So we just found out that x equals 4 and y equals 4 also doesn't work. But now if we let x be any value less than 4, or y be any value less than 4, and we take their fourth powers and add them, we're going to get something less than 512. Right? When x was equal to 4 and y was equal to 4, we were able to get 512. If we choose x and y to be either of them to be smaller than 4, then we're just going to get a sum that's less than 512. It's going to move us farther away from 625. So, you know, if y is 5, well, then x had to be 0. That doesn't work. If y is 6, that's going to be way too large. So y has to be less than 5, so y could be 4. But if y is 4, the largest we can take x is 4, and that's not going to be large enough, and everything just gets smaller. So if you consider all of these cases for what x and y could be, you can just conclude sort of by brute force that there are no values that satisfy this particular equation. So this sort of concludes the unit on simple proof techniques, and the next set of modules are going to focus on a powerful proof technique called proof by induction, and that's going to let us solve some really interesting mathematical problems.